Hi Mindsetters, and welcome back. Well, actually welcome grade 10,
Yes,
should we say?
absolutely.
Yeah, it's fantastic. This is the first of our live shows, grade 10. So glad you're joining in. We've got physical science up and Tracy is here. And she's going to teach us some amazing things today.
Well, I hope so. We're going to look about a little bit of history of the atom and a little bit of theory. Hopefully get those questions, you know, the ones in grade 9 when you go, why? And your teacher goes, just learn it. We're hoping to solve those for you today and look at a bit of electronic structure, and then we'll go from there. So there's a lot of stuff we need to get through, but I think it's going to be interesting. We'll see how it goes.
I think it's going to be a good lesson.
Yeah.
Guys, join us on facebook.com/learnextra. Also chat to us on Twitter @learnextra. Get your questions in. Yeah, and we'll see you after the break, and stay stuck to your seats. Yeah.
Yes.
We are so excited about today's lesson. Well, I am. I've already been laughing in the break with Tracy. It's going to be hysterical. It's going to be a good one. I've just been looking at the page. Guys, get those questions in. Come in, say hello, chat to us. If there's anything you want to ask me or Tracy or even our production team, I'm sure we could get them to answer, but the answers won't be that good. Guys, I know that we've got a few questions on what we're going over today, and I know that Tokozani has a question. He wants us to explain electronegativity in the elements of the periodic table. Tracy's going to tell us about this and when we're going to go over it. So let's start the lesson.
Sure. Thanks, Indiana. Well, Tokozani, I'm really glad you're already looking at the periodic table, and obviously this is something that's come up, and more than likely your teacher's gone over it already, but it's a little ahead of where we are for today. So I'm not going to jump into it just yet, just because we need to first build some foundation, get some trends in the periodic table, and we're going to do that next week. Okay, so we're going to look at the periodic table and all those things to do with trends next week. So hang on to that question. It's a great question, and it's got to do with electrons, but first we've got to look at electron structure, because talking about electronegativity doesn't make sense if we don't understand the structure. Okay, so I'm hoping that settles it a little bit for him or her. I'm really bad with this.
I think it's a him.
I'm sorry. Now what we're going to do is we're going to start by looking at models of the atom. Now grade 10s, I personally really like this section. Now I know most of you I took science, not history, which I can understand, but lucky for you, this isn't actually examinable. But why do you need to know about the history of the atom? Because you know, you get into your science classroom, and particularly in grade 8 to 9, and we tend to tell you, well, this is the way it is, and this is how it works, and just learn it. And you know, it's important for you to realize that our understanding of the atom is constantly changing. Our understanding of how the world works around us is constantly changing. And what we teach you didn't just drop out of the sky one day and magically arrive in a textbook and there we go. But there's a long history behind the atom and our understanding of it. And even then, you know, your grandchildren could very well be taught a very different model, because it's constantly changing, and that's what some scientists are spending their entire lives doing. So we're going to do a little bit of a brief history lesson, going way back to 5 BC to two Greek philosophers. And in ancient Greece, the philosophers were scientists, were mathematicians, they did everything basically. They were the clever people. And it was Democritus and Leucippus. I'm not really good with the Greek.
Leucippus.
Thank you. Yeah, I didn't learn Greek or Latin, but I teach it apparently. Now, their idea, which was actually incredible, considering this is 5 BC, no equipment like we have, they're the ones who first came up with the idea that the atom, that very small particle, is actually an indivisible thing. Okay, they weren't sure about its size, and they didn't really know what it was made up of, but they knew that it was indivisible. That was what their theory was. Now, over the many years, and it took us another 2,000 years almost to get to a different model, okay, we kept that, and scientists started to discover stuff. Now, what we're going to do, and I put the definition for you, is that all we're looking at is a model. And a model is simply a representation of a system. So it's a way for us to understand the real world. It's by no means definitive. It by no means says this is exactly how it works. And in fact, there's still a lot of debate within the scientific community as to what is happening within the atom. Okay, so it's a little iffy sometimes, so we're going to stick with the basics. Now, the first important person that we come across is a man by the name of John Dalton. Now, I've got quite a nice picture of him, not you, of him. And this is around 1803, so you're looking at 200 years ago. His idea was very similar to Democritus, and he did this from experimentation, and he was actually a British school teacher, so we're quite proud of him, all right? And he said that what the atom was a solid ball. In fact, sometimes it's known as the billiard ball model because it's like a snooker ball, okay? Solid ball, one big mass, okay? Which was great for a while, but then scientists realized it doesn't explain everything. So we get to our next scientist, who is J.J. Thomson. Now, his model was even better, but his model got a really cute little name. It got called the plum pudding model. He was a British scientist, and it's called the plum pudding model because he thought it looked like a plum pudding, where you have almost like a cake where the middle is positive, and then inside, dotted all around like plums in a pudding, you have our negative electrons. Now, this was great because he started to understand the fact that now we have a positive and a negative side to our atom. He thought that positive had no mass whatsoever, and that the electrons gave all the mass, and he thought there were thousands of electrons inside each atom. So now we get into the idea that the atom isn't the solid ball. In fact, there's other little pieces in it. And considering you're looking at 1895, where X-rays, microscopes, not like we have now, this is actually quite incredible. So he had this idea, and that was great. But then along came a man by the name of Ernest Rutherford. Now, what he realized was actually J.J. Thomson's model is a problem because he did a really important experiment. We're not going to spend too much time on it, known as Rutherford's scattering experiment, where he took very, very thin foils, like tin foil of gold, and he shot particles at it and saw what happened. And then the particles deflected, and he went, that's not really what should have happened. If it was the model of Thomson, then the particles should have gone straight through. And he realized, actually, here's now close to our idea where we have our positive nucleus in the middle and our electrons orbiting it. Now, this picture is very close to the one you often see on the net when they represent atoms and electrons. They will show these little spaces, and this is actually where the debate is at the moment as to what the electrons do, not that, around the inside of the atom. But we're not too worried about that right now. And this was a huge leap forward for us, because not only did he realize the electrons are orbiting it, but he's the one who then realized, hang on, wait, they're not thousands of electrons. Electrons can be counted in the tens. So instead of having thousands, atoms now only had 1 or 2 or 3, or at most, according to our current periodic table, about 119. So this was huge. Because now scientists are going, but now, where does the mass come from? Where does if the electrons gave the mass, and now we're saying there's so few of them, what is actually happening in there? And this is where it starts to get interesting, because we then go on to a man by the name of Niels Bohr. Now, he is responsible, I'm afraid, grade 10s, for a lot of your headaches in grade 10, because what he realized is he's the one who said, well, the nucleus is in the middle, and this is a much better representation of the size of the nucleus, okay? It's a tiny little dot, and in fact, in most textbooks, the dot we draw for the nucleus is far too big. And to give you an idea of how big it is if we had to go and take a pea, just the garden variety frozen pea, and put it in the middle of a soccer stadium, and then put you as the first electron right on the edge, on the outside of the stadium, you're still too close. Okay, that still doesn't show the difference in size. So this is magnificently small, and that's what makes it so hard to come up with a theory that we can turn into a law. It's why we use a model, okay? But now what Niels Bohr realized, he said, well, you know, inside the nucleus, we have the nucleus, which is positively charged, as well as, and Rutherford did some of this as well, is we have neutrons, those neutral particles. The electrons orbit our nucleus at set distances. So it's not just an arbitrary, oh, well, they are where they are, but they're at set distances. And that's the essence of where we need to get to today, is that these set distances are very specific, and they're called orbitals. And we are going to talk about where the orbitals go and the size and that sort of stuff. But each of these orbitals have an energy level. So the electrons have a certain amount of energy depending on how close they are to the nucleus. Okay, which was really important for us because this model, in fact, Bohr's model is the best model we use when it comes to things like bonding. Why is it that sodium and chlorine bond the way they do? Okay, so that's the question we need to ask. Or why is that water in water, why does hydrogen and oxygen bond the way they do? And I'm sure you've heard somewhere along the line in the last little while you've started your grade 10 is things like table salt, sodium chloride. It's a very hard solid, okay, and it's got a very specific bond. It's ionic, whereas water, you know, is a liquid at the same temperature, and it's runny. Why? Because of their structure. So that's what we've got to get to. So first we've got to understand what the structure does, okay? Now, what I have here is a quick question, and it's just a bit of a history question, and also I put it in here deliberately because when you look at a question like this, and it's a match the column, which you probably won't get very often, is I'm hoping you're looking at this, go, okay, now we can do some of this. We looked at some of this today, but hang on, wait. We're seeing a name I didn't mention. And you're going to go, oh, no, I can't do it. I haven't learned that, so I just can't. I did it deliberately because often, this is almost like a multiple choice type question, so I'm going to give you a little bit of exam technique. As you look at a question like this and you give up because you go, for example, I didn't talk about Marie and Pierre Curie at all, and I didn't talk about the discovery of radiation. And you're going, maybe those two go together. But let's think about the others, okay? So the discovery of electrons and the plum pudding model. I hope somebody's actually shouting it out at me.
Plum pudding.
Plum pudding, yeah, that's
I do have quite an interesting question here.
Yes.
Vusani wants to know, is the type of model named named of the person, I'm guessing, named after the person, but obviously the plum pudding one.
Oh, that was just his, yeah.
Yeah.
Some of them are.
So they decided what they wanted to call their...
Yeah, it's more like a nickname than a real model. I think he would turn in his grave if he knew we called it that.
Yeah.
But Bohr's model is definitely, Niels Bohr is actually, he was a German scientist. In fact, they made stamps to honor him. It was huge. It had a big impact, and that was early 1900s, so it was quite a big thing. Yeah, a lot of the stuff we name after scientists, but that doesn't happen as often anymore. It only happens generally with your scientists from the 17, 18, 19 centuries. Nowadays, there's too many of them and happens too often.
Yeah, exactly.
And, we don't learn
every
about
new
those.
Discovery.
Hey? We could never keep up.
The Indiana. I like that, hey? The Indiana. You have to discover something now, guys.
Or you can just have a unit named after you.
Oh, that sounds
like
fancy.
Kelvin or volts when we do electricity, Voltaire. But he was a bit cooked in the head. That's a story for another day. When we get to electricity, hang 10, grade 10s, we have a good story for that one.
Exciting
Includes
stuff.
little boys and frogs' legs, and they were a bit cooked in the head back then. Anyway, moving on. So let's answer the question, shall we? So, discovery of electrons and the plum pudding model, we've already discussed it. That would be D. J.J. Thomson. Brilliant. Arrangement of the electrons, which we've just spoken about, that would be Niels Bohr, so that's great. Atom, as the smallest building block, is our ancient Greeks and Dalton. And then discovering the nucleus was Rutherford, okay? Now, Marie Curie and Pierre Curie, discovery of radiation. Marie Curie is also one of those interesting ladies who sort of got into it by accident in some ways. They discovered radiation by accident. In fact, they're the ones who discovered X-rays. And she was the first woman to actually get a Nobel Prize. And without her, Rutherford would never have discovered the nucleus. So girls, hang in there. Girls are actually quite important. Okay, it's just not always given a lot of credit because that was the society they lived in, unfortunately. Okay, so we've done a brief little bit of history of where it is and where we're going. And do we have any questions on the history, or should we take a little bit of a break and then we'll come back and do atomic mass?
I think what we shall do is we'll take a break, guys. We're going to go through your page. I'll have a look at what you've been chatting about. Please follow us on facebook.com/learnextra. That's learn XTRA. Also at learn extra. The page is very quiet. Grade 10s, where are you? Even if you want to say hello or what's up, let me know. Grade 12s, are you guys joining in? Hey? You know, yesterday lots of grade 12s joined in. Like, there were actually more grade 12s than grade 10s, but that's a secret. Okay, so grade 10s, do us proud and stick to your seats, and we'll be back in 2 seconds. Bye. Hi guys, welcome back. We've been having such fun. We've been laughing here in studio. We've been chatting about atoms. I know somebody on the page said to me, they said, does the human body have atoms? Tracy, does the human body have atoms?
We do, I'm afraid to say. Some of us have more than others. And in fact, we just looked it up, and apparently according to the website, there's 7 times 10 to the 27, which is 7, with 27 little noughts underneath. Lots and lots and lots, which we're quite grateful for.
Millions and millions and millions.
Millions and millions and millions, because remember, atoms are the smallest thing. So all of us, all arranged differently. And in fact, what would be a good, interesting exercise is, I know you can find it, I'm just not sure how you would Google it on the net, is you can actually go and look up how much the human body is worth in terms of real value, like when you cost, and it's been done somewhere where they break down what elements all the human is made of. And remember, we're about 70% water, so most of that is hydrogen and oxygen. So if you really think about it, when somebody says that you're full of hot air, you actually might be, which is a bit rude. But anyway, moving on. So let's get back to our atoms, okay? So now we've got to the basic history. Let's get down to the nitty-gritty. The first concept we really need to deal with is atomic mass. Atoms are ridiculously tiny. So when it came to atomic mass, scientists had to find something to compare. It couldn't just be that, it's not like you can take an atom and put it on a scale, which would be really nice, but you can't. So atom originally, when they decided to do atomic mass, it was a relative scale. Relative just means they chose something as the standard and they compared everything to it. That original scale was hydrogen because they knew that hydrogen was the smallest element at the time. However, hydrogen's not that stable in relative terms, and there's not that much of it compared to other elements. So now we compare it to carbon, okay? And in fact, our definition is that I haven't put it there, but we compare it to carbon-12, and carbon is our most stable element, and it is the most abundant element. It is found in so many different forms. So we compare it to carbon. Carbon has atomic mass of 12, which is atomic mass units. It's not grams, it's not kilograms, it's a new unit because it's comparative. And that 12 comes from the fact that it's actually 12 times bigger than hydrogen, but now we set it as the standard. So on any periodic table, and I actually have one here, is we put the atomic mass units on here. Now, the nice thing is you don't have to learn these, though by the time you get to grade 12, there are some you get to know off your head because you're going to use them so often. So hydrogen is 101, lithium is 101.01, lithium is 6.94. We're going to talk about where the comma comes from because that's quite important. Carbon is 12, nitrogen is 14. And on this periodic table, which is very similar to the one you should be getting as your information sheets, it's at the bottom. Please, you've got to learn. You don't have to learn the key, but you must be able to read it. So the key, according to my periodic table that we're using, is the AMU's atomic mass units. EN is the electronegatividity, which came up earlier, which we'll talk about later. And NO is the number Okay, they're really talking about number, it's its position, it's also where it's number of protons and electrons. Okay? So you don't have to learn atomic masses, you never have to learn those, but they are relative and they change depending on the element. And the bigger the element, the bigger its atomic mass. Now, as a comparative scale, one atomic mass unit is equal to 1.67 times 10 to the minus 27 kilograms. So that's the opposite end of the scale compared to how many atoms we have in the body, because this is minus 27, so it's 0, 26 zeros, then the 1.67. It's ridiculously tiny. Okay, but inside the atom, we have 3 important particles. Now, there are hundreds others, and they are for varsity, so we're not going to worry about those. We have the electron, which is what sits around the outside and does all its own little thing. Its mass is 9.11 times 10 to the minus 31 kilograms. It is tiny, okay? It has a unit charge of -1, but in coulombs, it's minus 1.6 times 10 to the minus 19 coulombs. Now, you're saying to yourselves, I'm sure, do I have to learn those numbers? No, you don't. They will be given to you on an information sheet, okay? But like a lot of the other things, by the time you get to grade 12, you are going to know them because you're going to use them often. It's just a comparative scale at this point, okay? Inside the nucleus, we have protons, which have got a mass of 1.6272 times 10 to the minus 27. Now, I want you to see something, grade 10s. If you look at the mass of your electron, it's minus 34. Mass of the proton is minus 27, okay? That is 10,000 times difference, okay? So what I'm saying to you is the proton doesn't add mass. That is not its function in the atom at all. The electron doesn't add mass. The electron adds its size, okay? The electron floats around, does its own little thing, and gives it its size, and that's what we like. The proton gives it its mass as well as the neutron, because the neutron is very similar. It's slightly heavier, but it's the same thing. The neutron has a charge of plus 1.6 times 10 to the minus 19. Same charge as an electron, and I'm hoping you remember this from electrostatics from last year, that inside an atom, your protons and electrons must be equal for a neutral charge. As soon as I take electrons away, which we can't do through friction, okay, then we're left with positive charges. One thing is left positive, one becomes negative, okay? And your neutron has no charge, okay? It adds mass. So we're not overly concerned about our neutrons. It doesn't have too much to do with our models of the atom, but it's then we do need to know what they stand for. And in any element, and this is important for you to get, an element essentially on our periodic table, if we look at it, if we go there, is defined, this number in the top left-hand corner, that number is defined by the number of protons in an element. So the fact that hydrogen is different to helium is because helium has 2 protons, hydrogen has 1. I can make hydrogen's electron structure look like helium by adding an electron to it. But it's not helium. It just has the same number of electrons. It's still hydrogen because it has 1 proton in its nucleus. Okay, that's really important that you get that. Now, where does that lead us to?
Can I ask you a question, Tracy? Don't you want to go back to your beautiful periodic table?
Oh, my periodic table?
Just love it.
Yep.
Got a few questions?
Our friend. Yes.
Treasure wants to know who created the periodic table.
Actually, it's also one of my favorite stories. That's by a Russian...
We could be here a while.
We could, yes.
Thanks, Treasure.
I'm sorry, Treasure. You've hit the nail. I love the history.
No, it's a good question.
It's Dmitry Mendeleev, which was first discovered in the 1800s. It's late 1800s. And actually, the story is quite interesting because what he did, and if you actually Google periodic table, you'll find you can get all sorts of types of periodic tables. And this is what makes it so incredible, is they didn't know all the elements at all, and there were lots of spaces. And what he did is he did it like a jigsaw puzzle. So he took all the elements that he knew on little cards, essentially, and wrote down what he knew about them. Properties, what they looked like, what their mass was, what their chemical properties, and then sat and worked out trends and what looked the same, and he eventually came up with this format. And in fact, he left blank spaces. He was like, no, we haven't discovered that element yet, so we're going to leave it blank. And he was about 90% correct in his predictions on what those elements would look like, what their chemical reactions would be like. So we've had it around for 150 years, and it's not going to change anytime soon, not this version of it. We sometimes change what information we put on it, but this format is the one we're going to use because it's the most informative for us, you know?
That's amazing.
I think it,
and then I
to be that
know,
clever. Yes.
this is another thing, and then I'm going to let you carry on.
No, no problem.
I just thought I should share. Leighton James said hydrogen is the lightest element known to man.
Yes, it is.
Yes, just a little bit of fact for the day.
Absolutely.
Thanks,
'cause it's
Leighton.
number one.
Thanks.
And it is the lightest, and it's a gas.
Yeah.
Hydrogen is a very special one. We have lots of very special elements, but we'll get to those next time. In fact, yeah, no, we won't do that now. I like to talk to myself sometimes when I'm
I know,
teaching.
but there's just so much
You know,
interesting.
I love the periodic
stuff
table.
to
This
talk-
is
yeah.
our friend.
Yeah.
In fact, I tell my kids, and this is a good idea, grade 10s, if you don't have a paper copy of your periodic table, go make a copy of the one in your book. Okay, make sure you have one. And as you learn about it, color things in, make it colorful, use a key. This is your best friend in chemistry. In any any chemistry test or an exam, you really should be given a periodic table. You're not expected to know it off by heart. You're really not. And this is your best friend because he will do so much for you. He's great.
What is Tabocha wants to know, what is the guy's name again?
Dmitry Mendeleev.
Dmitry Mendeleev. I'll
Yes,
find that and post it on Facebook.
He's got
Yeah.
a nice big beard and he's a great. His story is actually quite incredible.
That is amazing.
All right, so let's go back to the atom. So, I'm hoping this doesn't look unusual to some of you. This is what we call standard notation in a lot of ways. This is how we represent elements, and I'm sure you've seen this somewhere in your textbooks. Now, whenever we represent an element, we have its chemical symbol, H, Br, whatever, which you should have learned a lot of those last year. And then we represent the atomic number, which we put at the bottom, that's the Z, and the atomic number is the number of protons in an atom. If it is a neutral atom, then the atomic number is also representing the number of electrons. At the top, we have the mass number, A. Now, the mass number tells us the number of nucleons. Now, I've introduced a new word. Nucleons is just the collective word for protons and neutrons together. Okay? So if we go back now, I'm going to do some writing. So if we go here and I tell you, well, and I've got some examples, I don't always remember all of them off by heart. Unfortunately, I wish I could. So if, for example, I'll give you this, and we'll look at something, maybe I should have a pen, and we do 11H, that's hydrogen. Okay? Now, what that means for me is hydrogen over here has a 1 proton and 1 nucleon. So looking at this, how many neutrons does this proton atom have? Well, it has 1 proton and 1 nucleon, so 0. Okay, because the number of neutrons, so if we write it down for you. So, wow. This board doesn't like me, by the way. I'm just going to make that official.
It doesn't like anyone, I think. You've got to love it.
I do love this board.
Tracy,
though.
love it and respect it. Because it's your sleeve.
It's my sleeve.
Don't worry, mine's just her sleeve. She'll get it. Hey, see, perfect.
There we go. Number of neutrons
Yeah, perfect.
is
You've
equal
got
to
it.
your mass number minus your atomic number. So if we look at this one, it's 1 minus 1. Okay, so that's equal to 0. Let's do another one which doesn't look quite like a dog's breakfast, shall we? Okay, how about let's look at this one, potassium. And potassium's a nice element. I'm hoping you remember those experiments from last year. Go, well, this one's much bigger. And now potassium has 19 protons, and in the neutral atom, maybe it's got 19 electrons. And now we go, how many neutrons would it have? Well, it's a bit of a math sum. Use your calculator because it always makes life easier. So another way of us representing neutrons without actually having to write it out is an N with a little 0 on it, because that means it has no charge. And we will then go, well, man, there we go. 39 minus 19, which is 20. That has lots of neutrons. There's no set trend to say that the bigger it gets, the more neutrons it has compared to protons. Generally speaking, you will have the same number of neutrons as protons, though there are exceptions, and then every now and then you get some with more. Okay, so it's not, you can't really learn a trend for that one, unfortunately. Okay, so let's do a little bit more. Okay, but now we're going to look at the concept of an isotope. Isotopes are interesting little things for us. It's a new word for you. Please learn it. You're going to get a whole bunch of interesting words. You get isotopes, you get isomers, and you get allotropes. Okay? You never have to worry about allotropes at school anymore. Isomers you're only going to worry about when you get to grade 12, so all we worried about are isotopes. Now, what an isotope is that elements, it's been discovered that elements can have the same number of protons but a different number of electrons, okay? And that's actually quite important, because when the number of neutrons change, the mass changes with it. And that explains for us why, when you look at the mass number on here, these aren't whole numbers. When I've just said to you that when we write it, we're going to go mass number and your number of protons, okay? So it should actually give you a whole number, but it doesn't, because this number, this atomic mass unit, is what we call, it's worked out statistically, which we're not going to worry too much about. So they look at the percentage of each of them, okay? So if there's a high percentage of one or a low percentage of another isotope, and then they add it all together and they get the average, basically, but it's a statistical average. It's not a fun calculation, so we're not going to worry about it. Okay, so this doesn't help me when I want to calculate the number of neutrons. So this doesn't help us. So in a test or an exam, they actually have to give it to you in this format. Okay, so that's the format you need to do your calculations. Okay? You guys all coping with this, I hope? They're not screaming at us on Facebook just yet?
No, not yet.
I'm hoping I haven't done anything. Okay.
Yeah, I might stop you, can you imagine? Stop, Tracy.
Okay, in fact, this is actually a good place to take a break if we can, because then we're going to get onto electron structure. And
I think
pretty sure that's going to...
Okay, guys, let's take a quick break, and we'll be back in a few seconds.
Yeah.
Okay, see you now. Welcome back, Mindsetters. I'm so excited that you're back, because we've only got 10 minutes left. And instead of Tracy going over something new, we've decided to leave it until next week. And what we're going to focus on now is your Facebook questions and your Twitter questions. So I'm going to go scroll all the way down and start asking Tracy. This is going to be fun. I'm going to put it on the spot, guys. This is going to be exciting. No pressure at all, Tracy. Brilliant. So guys, please get your questions in. We've literally got like 8 minutes now. It's www.facebook.com/learnxtra, and then also @learnxtra for Twitter. So get those questions in, and I'm going to make sure my eyes are peeled to the screen. So are you ready?
Absolutely. And there's no such thing as a stupid question.
Exactly.
Because someone's going to ask a stupid question you're thinking of, I promise.
Exactly. And that's what I always say. I think, let's start with Mampali. Mm-hmm. She wants to know, is the number of electrons in an atom equal to the number of neutrons?
No, not always. That depends on your mass number, okay? What you do need to remember there, Mampali, and it's a really important concept, is that maybe I should actually have a pen, how does that sound? Your atomic number, okay, that number, your 19, the number of electrons is always equal to the number of protons. The number of neutrons can change. And sometimes, like with potassium, it's bigger than the number of electrons. Sometimes it's not. It all depends, okay? So it's equal to the number of protons, not neutrons. Neutrons don't have a charge, so they're just there to add mass. They don't make much difference. So I hope that helps.
Yeah, I'm sure it does. Big time. Lorato wants to know, is it important to learn all the names of the people who created the atoms?
No. Look, this is also going to be a bit of a teacher thing. According to the curriculum, it's not examinable. Bore you're going to hear lots of. It really is just for interest. It's to give you the background and to know where we came from. And I think understanding it's more important than actually knowing. You don't have to know the dates and times. It's not history, which is a good thing. Yeah.
It's amazing. Okay.
Yeah.
Let me see. What else? Okay. What is a chemical formula for ammonium sulfate? Does it have to do with what we're talking about?
Not at the moment, but it's quite easy. Ammonium sulfate, I can do that in 2 seconds, is NH4. I'm not sure if that's a grade 10, but that's okay.
This is Tubbing. Mine as well.
Yes,
There you go.
NH4 to SO4. Okay, but we are going to deal with how to make that because you did a little bit of that in grade 9. You would have done some formula making. And in fact, next week when we do the periodic table, that will start to make sense because I'm pretty sure your teachers just learn the rules.
Do you want a funny one?
Where they come from. Yes.
Do you want a funny one from Mpho?
Let's hear this.
Okay, in which country do we find the most famous scientists?
Oh my word. Well, actually, a lot of them come from South Africa, by the way. Recently, South Africa, despite what we think sometimes, we have a very rich history in terms of technological in development and scientific history and development. And remember, we're actually busy trying to get the square kilometre array, which is, hopefully we get it and beat Australia, which will be even better.
Amazing. Okay.
Absolutely.
From Kitonsa. Katonsa, I'm sorry I can't say your name. Katonsa Charles.
There we go.
Why is hydrogen found in both group 1 and in group 7?
That's actually quite an interesting one. We won't, it all depends on how we set up the periodic table. We tend to put it in group 1 because of its electron structure, okay, and it really should be in group 1. If you look at any periodic table, it shouldn't actually ever be put in group 7. It probably floats above it. It's also because hydrogens are non-metal, and all our metals sit on the left-hand side, whereas our non-metals sit on the right-hand side. So that's where it doesn't really fit in group 1, but it doesn't fit in group 7 either. It's just a good place to put it because of its structure. So it's a easy answer, really.
Okay.
Fits into both.
Malloy wants to know, can you make helium solid?
Possibly. That's an interesting question.
Am I asking you these hard...
No.
These mindsets ask some
These are good
strange questions.
It doesn't really fit in with what we're doing. Helium is... It would be very difficult. It does have a melting point. I don't know what that is, though, but it would be extremely cold. You'd be looking at minus 200 or more degrees Celsius. So you could, but it would be difficult. Very difficult. Lots of pressure.
Okay, Tracy,
Yeah.
hopefully, if any of my questions don't have anything to do with what we're talking about, guys, no, I'm sorry, Tracy.
It's okay.
And then also mindset is please send me relevant questions. When we're talking about a topic, it's much easier because there's me all over the page trying to go, okay, this, and I'm going to confuse poor Tracy. Let's
That's okay.
stop
Sounds like my own classroom.
I'm telling you. Peter Finn wants to ask, may I ask what is the standard atomic weight in an element?
Okay, I think you're getting confused with mass and weight, okay? There's no such thing as standard atomic weight, per se. I think you're talking about standard atomic mass, and that's relative atomic mass, and that's what's given on our periodic table. Okay, so that doesn't really exist, and it would be a comparison. So if it's being used as a way to teach you something, it's being used as a comparison. So we don't really have that. We have standard temperature and pressure, but no such thing as standard atomic weight. And we'd rather use mass because weight is a force. Yeah.
Okay, we've got another one from Peter Finn. I thought it was quite funny because he said, hydrogen is a non-metal, so why is it in group 1? But Mandler's answer was,
Yes.
Hydrogen is special, dude.
And that's just it. It is. It's special. But as I said just now, Hydrogen's in group 1 because of its structure.
Because of its structure.
Because it has that one little lone electron chain, which leaves it quite often, actually. And all of group 1 elements, when we get there next week, you'll see, has one little electron that leaves it quite often. So it has a similar structure, which is why we put it there.
So it is special.
It is very special. Hydrogen's
Dude.
great. It's a special dude, man.
It's a special dude.
Absolutely. I'm okay with that.
Oh, it's so funny. Okay, Kutjo wants to know, why don't neutrons have a charge?
I actually wish I knew that answer. But it's a good question. I don't know.
We'll find out.
Yeah,
Okay.
I think it's going to come down to one of the answers where you go, that's just the way it is, I'm afraid.
Okay.
Yeah, no answer to that one, but it has a very important function.
When was carbon? Okay, the timber. We've got
Yes.
5 minutes left.
And yeah, this is going to be one of
Yeah.
those.
3 minutes left. Okay, when was carbon discovered and how was it discovered?
I haven't a clue.
Oh, I was waiting for a big story. I was like, Tracy.
That's one I don't know.
I was like, Tracy's totally gonna have a big, large story
no,
for
I'm
me.
sorry. That won't put me on the spot. No, but that would be an interesting question. But remember, it depends on whether you're looking at carbon as coal, carbon as diamonds, carbon as graphite. Carbon has lots of ways of being, which is actually why we use it as a standard. It's why it's the relative atomic mass. In fact, we can use it as a lot of standards. Yeah.
Okay, let's see. Where does it say? It says, can you please explain this? Why the symbols have positive and negative numbers next to them? I'm not quite sure.
Okay.
This is from Timothy.
No, I think what Timothy is referring to is whether, for example, I give you and I say to you, well, now we have potassium, and I tell, let's do this, and potassium ends up, often will be written as K plus. Now, Timothy, if that happens, what we're actually indicating to you is that that potassium has lost electrons and has lost one, okay? But potassium can't lose a random amount of electrons, it can only lose one, okay? Whereas sometimes with something like, jeez, the red pen really doesn't like me. Yep, the chlorine, okay, Cl minus, is because the chlorine will take an electron. So the plus and the minus indicates that it's become an ion. It's lost or gained electrons, and the number depends on how many it's lost or gained, and that depends on the bonding. And that's going to come back down to structure, which is what we're going to look at. And so it all depends on whether it's lost or gained. And this means it's an ion. Okay, it hasn't changed, so Cl minus is still chlorine, it just has an extra friend, basically, is how it works. I hope that helps for Timothy.
That is amazing. We literally have 1 minute left.
Goodness.
Time
Yes.
has run out. Guys, I'm sorry, Tracy. I feel like I'm kicking you out.
I also feel like I'm being kicked out, but it's okay.
Because you guys know that I stay here all throughout. Anyway, guys, thank you so much. Grade 11s, don't forget, tune in next for physical sciences. And grade 10s, thank you so much for having such an awesome lesson with us today. We enjoyed ourselves thoroughly and hope to see you tomorrow or next week.